This is Bob. Bob runs a large business where he buys materials from a set of suppliers and sells his products on to a set of customers. The business is going really well, and Bob is rushed off his feet dealing with all his orders. Just this morning, though, Bob noticed that he'd received an invoice from one of his suppliers for £8,766. How can he be sure whether this invoice is for the correct amount or not? Good afternoon, everyone. My name is James Farr, and for the last 6 weeks, this is exactly the problem that I've been trying to solve. I've been developing systems to detect errors in invoice amounts. I've been working as part of Xelix, a company which offers an invoice intelligence platform, providing insight into its clients' invoice data and protecting against fraud and invoice error. Currently, Xelix are able to detect a variety of different errors, including duplicated invoices, incorrect invoice numbers, and incorrect supplier details. My work then was to extend their offering to include invoice amount error detection. Now, this kind of error can appear in a number of different forms. If we consider Bob's invoice once again, we see that this might have been the result of a missed decimal point, converting what should have been an invoice for £87.66 to the £8,766 that Bob received. Equally, there might have been a 1 missed from the start of the amount. A 0 might have been confused for a 6, or the supplier might have forgotten to add 20% VAT. Of these different error types, the most damaging for Bob is the first, where the decimal point was missed, because ultimately this means that he might overpay his supplier by more than £8,000. How then can we try and identify this error? Well, naturally, we might want to try and compare it to the other invoices that Bob has received from the same supplier. We might look at the distribution of invoice amount that that supplier has sent, or we could look at how many zeros are normally at the end of that supplier's invoice amounts. What we then hope is that correct invoices will sit nicely near to the peaks of these distributions, and indeed in Bob's case, the correct value of £87.66 sits in the middle of the distribution on the left and clearly matches most of the other invoices from this supplier in that it has no zeros at the end of the amount. On the other hand, we also hope that anomalous invoices will sit much closer to the edges of these distributions. In this case, the error value of £8,766 clearly sits near the edges of these two distributions and so should really immediately raise our suspicions. Bob, though, is a busy guy. He doesn't have time to look at these graphs for every single invoice he receives, and so he wants to automate this process. Traditionally, he might do this by feeding all of his invoices into a rule-based error detector, which uses a set of predetermined rules to flag potential amount error invoices. Typically, though, these systems produce a large number of false positives, invoices that are correct, but which the rule-based detector thinks might contain an error. Bob will have to then check through all of these invoices manually, meaning lots of work for Bob and making him thoroughly miserable. Fortunately, though, the story does not end here. The rule-based system struggles because it isn't flexible enough and can't pick up on the subtleties of amount errors. To address this then, we might seek to introduce a more naturally flexible machine learning error detector. This can then pick up on the intricate details of amount errors, producing far fewer false positives and putting Bob in a much better mood. The million-dollar question then is, how do we create this detector? Well, in this case, we start with a lot of data, 19 million historic invoices from Xelix's clients. In order to train our machine learning models, we'd then like to label these, either as amount errors or as correct invoices. One approach to do this is to try and identify reversals. In other words, where an invoice has been sent by a supplier, they then realized it was wrong, retracted their invoice, and finally sent a correct replacement invoice instead. Unfortunately, though, this is a very tricky process, and we can only surface 43 errors like the one Bob received, where he would have ended up overpaying his supplier enormously. This is nowhere near enough to train a machine learning algorithm, and so instead, I chose to introduce artificial errors, controlling the size and the type of the errors to enable my algorithms to learn meaningful patterns from the data. I then took a set of historic and artificial invoices, and for each one computed more than 200 features, comparing each invoice to the set of other invoices that Bob had received from the same supplier. I could then use these to train a variety of different machine learning models, of which I found that the best performing was an XGBoost classifier. Testing this on a set of unseen historic and artificial invoices, I could demonstrate that this has the potential to identify 64% of Bob's amount error invoices, and most importantly, could reduce Bob's capital loss due to amount errors by 96%. At the same time, it only required Bob to manually inspect 0.5% of his invoices, easing his workload, saving him time, and ultimately making him a very happy man indeed. Thank you very much for listening and enjoy the rest of the presentations.